Okay, all of you had a nice long weekend. Uh, if you have questions about test number 2, just let me know. Okay, either by email or we could meet over Zoom and discuss any of your questions. Just a reminder, we have test number 3 on Thursday on chapter 3. Okay, we are kind of still on 3.3 and 3.4, not completely done, but I hope got a chance to start the homework and see how that is going. Okay. So let me just remind you of a few things from last week. And if you have any questions about any of these, we were doing the Heaviside function, which is the 0-1 step function. Okay. And we could write a piecewise function in, if you just have 3 pieces, for example, 0 less than or equal to t less than t1. So if you have, say, 3 pieces which are continuous by itself, okay, so this is a piecewise continuous function, you could write this as f of t equal to f1 plus u of t minus t1 times f2 minus f1 plus u of t minus t2 times f3 minus f2. So the advantage of doing that is we could find the Laplace transform of each term, okay, using the second shifting theorem. So the Laplace of u of t minus a times f of t minus a is e to the power of negative as times f of s. So all these terms are kind of nicely set up to apply the second shifting theorem, and you could do this for how many other terms you want. Okay. So that is one of the many things we saw last week. Okay, and this is something that you could apply both back and forth. So the inverse of the second shifting theorem would be L inverse of e to the power of negative as times f of s. The only thing here to keep in mind is you have to shift your function by whatever amount you are delaying your input with, right? Your input was delayed accordingly here, here, and here. Okay, so when the output is given out here, make sure that f of t is not just staying as f of t, it's f of t minus a. Okay, that's a small detail that you would find in all these problems in sections 3.3 and 3.4. So that's pretty much where we stopped. Okay. Do you have any questions before we start today about this week's test or anything? Can people hear me online? Or?
Yes.
All right, good. Okay, so let's do an example just to get started, and then we could talk about more new things. Okay, so example, solve the initial value problem. Y double prime minus 9y, there's no y prime here, equal to u of t minus 2 with y of 0 equal to 1 and y prime of 0 equal to 1. So it's a problem with both initial conditions being non-zero. The only difference is that now the problem gets a little bit lengthier because of those two. Okay, so can you start this? And I think I forgot to write this one. The Laplace of u of t minus a is okay, so this is case number 11 in your table. This is case number 13. So can you just start and see how this goes? And I'll tell you a common mistake students make with this particular left-hand side sometimes. Hope all of you have your Laplace tables with you, printed or electronic. You need that here. This should be a first step. Okay. Most of these problems have a very common set of steps until you reach the last few places where you have to fill in all the details. Okay. These are pretty routine steps here. Please don't always assume that the initial values are always 0. Okay, here both are equal to 1. So this would be 1 here, and this would be 1 here. So that's going to be s square minus 9 ys minus s minus 1 . Oh, that's YF. That's what he meant. Sometimes my handwriting is a little weird with this S terms. Sorry about that. Now, don't do anything silly here. Okay, so be careful about this part here, which multiplies the YFS. This is not multiplying. Push it to the right side and then do what you want. Okay, all your basic algebra rules are still valid. So this is e to the power of negative 2s over s plus s plus 1. And then you can divide both sides by s squared minus 9. So whenever the initial values are not 0, it comes with extra work to do. Okay, because you could see there, if the initial values were both equal to 0, you wouldn't have had to deal with this block of term here. Okay, now we got this block and that block. Okay. I told you there is something that students get wrong in this kind of problem, and that's mainly because they think this term is something that you could easily invert using your table. Okay. So when you have, if it was s squared plus 9, for example, okay, this would be 1/3 of sine 3t. That is case number whatever, 6 or 7 in your Laplace table. And for some reason, students think that you could just write this as s squared plus negative 9 or something, okay, and write it as 1/3 of sine of negative 3t. That doesn't happen, unfortunately, okay, for reasons which are very basic algebraic. Okay, you cannot factor this into two terms as you might think. Okay, and this is something you could factor, right? So 1 over s squared minus 9 is the same as writing 1 over s plus 3 times s minus 3. So looks can be deceiving sometimes. Be careful. This is plus and that's a minus. Okay, this cannot be factored, this can be factored, but when you factor it, it also comes with a requirement of doing partial fractions later. Okay, so that's the only thing you have to be careful about here. Maybe it was obvious that you could do it, but in case you are looking at it this way, it's not right. Okay. So long story short, you have to factor that and write it like this: y of s equal to e to the power of negative 2s times 1 over s times s plus 3 times s minus 3 plus s plus 1 time divided by s plus 3 times s minus 3. A lot of students have made this mistake, and maybe it's just the anxiety during the test time or something that they think somehow they could just do this kind of magic there. Cannot. Which also means, unfortunately, we have to do two partial fractions here, okay, because this has an s in the denominator, this one does not. Okay, so let's call this as block 1 and 2. So you cannot just do one partial fraction and then just put it in the second one if they're two different terms. So this one requires a separate one than this one. So let's do partial fraction block 1. Not difficult, but it takes time to do this. It's 1 over s times s plus 3 times s minus 3 equal to so if you clear the fractions, you get 1 equal to a times s plus 3 times s minus 3 plus b s times s minus 3 plus c s times s plus 3. All right, do your usual cover up method. So s equal to 0 would cover up the second and third terms. Okay. You get a equal to negative 1 over 9, s equal to 3 would sort of, I'm finding c next time. Okay, s equal to 3 will give you, so it's going to be a 3 there and a 3 plus 3 here. That's 1 over 18. I should have had an 18 on the right side to clear it, but too late now. S equal to negative 3. Sort of first and third terms, and you get b equal to negative 1 over, no, b equal to some negative 6 times negative 2, that's positive. That's also 1 over 18, is that right? Okay. Okay, so that's there. Let's also do block number 2. Okay. And this is one of the reasons why sometimes on tests the initial values are given to be 0, because just to avoid this multiple partial fractions in the same problem. Okay, it's a good thing to do it during homework. A lot of unnecessary repeated things during the test. And that's equal to a over s plus 3. You can use the same letter a. Okay, you don't have to. If you want, you can change it d and d. That's up to you. Okay. A over s plus 3 plus b over s minus 3. And please unmute or chat or type in the chat window if you have any questions in between. Okay, because I'm kind of standing here, I cannot see that far. So clear the fraction again. You have s plus 1 equal to a times s minus 3 plus b times s plus 3. So if you set s equal to -3, you get -3 negatives. A equal to 1/3 and s equal to +3 gives you b equal to 2/3, 4/6. Overall, now we need to plug it back into that expression there. Okay, don't forget e to the power of -2s when you pull it down. So that's going to be y of s equal to e to the power of -2s times the first block, which was -1/9 over s, plus 1/18 over s plus 3, plus 1/18 over s minus 3. The second block does not have e to the power of negative as term. That's just going to be 1/3 over s plus 3, 2/3 over s minus 3. Now start inverting it term by term. Okay. Just remind yourself when you see this term, that is where the second shifting theorem has to be applied. Okay. So everything that multiplies this must be shifted. No shifting here. Okay. That's because these two terms came from the initial values. They didn't have to wait for the external force to start anyway. So no shifting required in those two terms. Anything that is multiplied with an e to the power of negative as, that is the one that requires shifting. Okay, just to keep in mind about where these things are. So y of t, e becomes u. That's going to be -1/9. That's a constant, nothing to shift there. Plus 1/18 e to the power of -3 times the same t minus 2. What will be the next term? Can somebody tell me? Good. So it's the same thing that you would do throughout chapter 3, except that you have to shift any term that is multiplied with this u. Okay. But these two terms are just ordinary terms. That's 1/3 e to the power of 3t plus 2/3. Where does that look the same? Oh, sorry. A over s plus 3 and b over s minus 3, right? That's a -3t. Sorry about that. So if this external force was not there, these would have been the two terms solving the system, right? But with the force that is coming in at t equal to 2, whatever initial contribution was there, that is still there, plus the delayed input term. So that is your final answer. So I think if you look at the homework solutions, there might be a couple of typos here or there where I might have forgotten to apply the shifting on a couple of exponential terms. I forgot which ones. Okay, if you see those, just assume that they're there. Yeah. I've been planning to fix those for the last 7 years or something. All right. Any questions on this one? Any questions on the second shifting theorem? Okay. All right. So one more new concept in this particular part of chapter 3, and after that we could kind of start creating all kinds of crazy examples. Okay. It's about impulse inputs. The word impulse stands for something that you do just at an instant of time. Okay. So instant force, like a electrical short circuit, or if you just take a baseball bat and hit something just once, okay, that is what we call as an impulse force and an instant force. So the idea is this: you apply, say, some function f of t at just one instant of time t equal to a. Okay, it's 0 on both sides of that particular time. Okay. And it's f of t equal to 0 for t less than a and t greater than a. So just like if you have a spring mass system, and if I just take a baseball bat and just hit it once, okay, so it's going to create some oscillation there, but it's not something that I can keep on doing. Okay, I just hit that at a particular time and then I just shut it off. Okay. How do we model this mathematically? Because whatever we have done so far just to be a continuous kind of a distribution, right? F of t equal to something. Even if we were doing the Heaviside function, it was for t less than a and t greater than or equal to a. This is f1, f2. Okay. That's not exactly what is going on here. This is only at a particular instant of time. So we need something weird and clever to take care of this particular situation. So somebody was smart enough to do this. Okay. His name was Paul Dirac. He introduced a function that does exactly what we are trying to do here. Okay. Denoted by this Greek letter delta, it's called the Dirac delta function. Won the Nobel Prize in Physics at the age of 31. So kind of tells you about how smart he was. Okay. Delta of t minus a equal to 0 for t not equal to a, and it's equal to infinity for t equal to a. Okay, that's a crazy function. If you look at it, one of the golden things you have learned in all kinds of math till now is that you cannot set something equal to infinity, but then he just said that this function is equal to infinity at this particular point. Okay. So if you look at the graph of this, it looks like a spike at t equal to a. Here, it's 0 here, 0 here. Just at this one particular instant, there is this huge infinite input. Okay, it doesn't have to be infinity all the time, but he just gives enough room so that you could give any amount of force at a particular time. So it's an idealized function of sorts. Okay, but you have to justify why this function works all the time, and that's what we should next take care of. Okay, so this goes to infinity here. This is 0 here and 0 here. So if it's the first time you're saying this, it looks very weird because a function cannot be equal to infinity. Okay? It's one of the basic things that you learn in math. It has to be a finite quantity. So let's define this in an official way. So here's the meaning of the Dirac delta function. So you take this rectangle with width of h and height 1 over h. Okay. So this area is now equal to 1. Yes, it's length times height. So it's h times 1 over h, that's 1. What we'll do is we will reduce the width of this rectangle, keeping the area equal to 1. Okay, so I'm going to reduce the width here, but that would mean that if you have to maintain the height or maintain the same area equal to 1, I have to increase the height. Keep doing that. Okay. So reduce the width, keep the area 1, means increase the height. Okay. Reduce the width even more. So each time you're reducing the width of this rectangle and keeping the area equal to 1, that means this height has to increase proportionately. Okay. So decrease the width. Means you have to increase the height so that the area is maintained at 1. This is h going to 0. This means 1 over h goes to where? As h is getting smaller and smaller and smaller, where is 1 over h going to? Infinity, right? That was Paul Dirac's idea. Okay? So he took this idealized system where you're kind of squishing this in. It doesn't have to be a rectangle like this. You could even take a Gaussian curve like this. Okay, and kind of spike it up like this, and at some point it just becomes a spike at that one point. So there are a lot of functions that will exhibit this behavior, and the important thing is to justify this mathematically. So the Dirac delta function we just put those in quotes because it's not really a function. Okay? It's not your traditional function where you give an input output in the one-to-one correspondence, right? So the Dirac delta function is an idealized distribution, almost like a probability distribution. Okay. Defined by delta of t minus a equal to 0 if t is not equal to a, and it's equal to infinity if t equal to a. With the following properties. And those two properties will make sure that there is some sanity to the situation. Okay. This infinity is not really going to take over your life at this point. You're going to keep it under control because of the following properties. One, the integral from negative infinity to infinity of the delta of t minus a dt, that's equal to 1. Okay. It's saying that even if that function is going to infinity at that point, okay, the total area under this graph is equal to 1. That's what I was trying to show there in that picture with the rectangle. Okay, the total area is 1, even if it's spiking up. The second property is that if you apply the Dirac delta function to some arbitrary function f of t, t dt equal to f of a. And that's because the function is equal to 0 at all other points except t equal to a. Okay. Because the delta function is equal to 0 when t is not equal to a. So kind of helps you just pick that one particular value of the function out of that product. Okay. All right, so those are the two properties which we are not going to prove in this class. It's beyond the scope of this course. Okay. But if you ever take a physics or quantum physics course or something, you will probably prove those results extensively because you need those things there. Okay. All right. So the first question is, what is Laplace transform of the delta function? Okay. And this is probably where you're going to be impressed with what Paul Dirac did, because this is probably going to give you. Oh, I didn't say the height is inverse of the width. I was considering a rectangle whose height is inverse of the width. I didn't say that the height is always inverse of the width. So consider a rectangle of this kind where the area is equal to 1. Okay, that was the way I constructed the rectangle. Okay. I want the area equal to 1, and I construct a rectangle that way. Okay, so it's not a property that the width is always the reciprocal of the height. All right, so let's start with our definition. This is the integral from 0 to infinity e to the power of negative st times our function dt. Don't forget that the Dirac delta function is 0 everywhere except t equal to a. Okay, so we could write this as the integral from negative infinity to 0 e to the power of negative st delta of t minus a dt plus the integral from 0 to infinity e to the power of negative st times delta of t minus a dt. I'm able to do this because this is equal to 0 anyway. So all I'm doing is just adding 0 to that function. I haven't changed anything. Okay, because a is somewhere between 0 to infinity. This part is before t equal to 0. Okay, so that function is equal to 0. The reason for doing this is because now we can combine the two parts into a single integral from negative infinity to infinity e to the power of negative st times delta of t minus a dt. Okay, that's because we are adding two definite integrals which are just being continuous over time. Okay. So this looks like a property 2 I wrote somewhere here. Okay, this is your delta function, this is your f of t. Property 2 that I wrote earlier was the following. Since I erased it, that's why I'm writing it again. Integral from negative infinity to infinity delta of t minus a times f of t dt equal to f of a. Okay. So it kind of uses the delta function to sift it through and pick out this one value. Okay. That's what it's doing. Out of all the values here, it just gets one value out of this particular integral. Okay. So this is your f of t, that is your delta of t minus a. And this property tells you that you could just replace your t by a. So it's going to be equal to e to the power of negative as. Okay. So the crazier the functions become, the Laplace transform becomes incredibly easy to apply. Okay. So if you look at case number 12, the Laplace transform of the delta function is e to the power of negative as. Heaviside function has an s in the denominator. This one does not. Okay, so please make sure that you're copying the right things when you do these problems. Okay. So this is case number 12. If you have never seen this function at all, okay, don't worry if it comes out as a little bit crazy to you. Why is the first expression equal to 0? That's because delta of t minus a is 0 for all t not equal to a. And since a is between 0 to infinity, this is how I'm doing it. This is 0, this is positive infinity, this is negative infinity, a is somewhere here. So this entire thing, the function is 0, it's 0 here, it's 0 here, it's just a spike in this part. So I added that particular term just so that I could combine the two and use the property of the delta function. Okay. Is it clear? All right, thanks. Okay, so let's solve this problem here and try to get some idea about what's going on. Okay. Solve the initial value problem. Y prime equal to delta of t minus a, where y of 0 equal to 0. I'm trying to find the integral of the delta function, or what function when you try to take the derivative would give you the delta function. Well, let's just solve it using Laplace transform. So L of y prime equal to L of delta t minus a. It's the first derivative, it's not y double prime. Okay. So things are a little bit more easier here. So it's s y of s minus y of 0 equal to what I just wrote there, case number 12. That's going to be e to the power of negative as. Y of 0 is 0 here. Okay, I'm starting with no displacement initially. So this term is 0. So what you get is s times y of s equal to e to the power of negative as. Divide both sides by s. Now that's not a very unfamiliar Laplace transform. If you just look above, case number 12, you'll see this one, right? What is that function?
Step function.
Yes, it's u of t minus a. Okay. That's your Heaviside function. Okay. So these functions are related in a very deep, mysterious way. Okay. You won't probably see this in calculus 1. Nobody talks about the derivative of this being delta function because these are unusual functions. But for our purposes, now we can start believing that the derivative of the Heaviside unit step function is the Dirac delta function. This is what you call as operational calculus. Okay, so you don't see this in calculus 1 or 2 because these are completely weird and crazy functions, but this is true as long as you satisfy the conditions of these two functions consistently. Okay. What else does this tell you? Well, don't forget the delta function is an impulse input. Okay, it's just an input that you give at a particular instant of time. Instant input, and that is where your output starts. So if you're hitting something at t equal to 5, okay, you shouldn't be feeling anything before that. All the output or all the effect of that input should be felt after that. Okay. So the effect of this is felt. So this is at t equal to a. Instant input at t equal to a, the effect is felt after t equal to a. Okay. Makes sense, right? If you hit a baseball with a bat, all the movement for that ball happens from the instant you hit the baseball with the bat. Before that, there's nothing going on. Okay, so that is why this is the instant input. The output is the Heaviside function. Okay, so that's always the behavior that you should expect in these problems. Okay. The input is here at t equal to a. The output starts here from this point. So this is your electrical short circuit. All the fire happens after that. Or if you punch somebody, the pain starts after that. So all these examples which are the same effect. So why am I saying this? Because when you do a problem, okay, you should never have delta in your answer, ever. Okay. All your input is going to be in the form of delta, output is in the form of u. So you will never have delta of t minus a in your answer. And that's because that's an input that you give at a particular instant. Okay, the effect of that should be felt over time and not just for that instant, which is what this function denotes. Okay. Well, apart from the fact that it's a crazy function, okay, the problems using delta function are probably one of the easiest you could do in this chapter. Okay. So unless you're going to do research on what the delta function really means, these are really easy things to work through if you know your algebra pretty well. So you don't have to worry about that part. Okay. So let's do some examples. Any questions about the delta function or its meaning? If you want to know more about it, we could talk about during office hours or something, because I don't want to make it too intense in terms of the deep meanings of this function. Examples: spring mass system with damping. Okay. As m equal to 1, c equal to 6, and k equal to 13. Okay. I think those are nice numbers. An input of 5 units is applied at t equal to 3 and shut off. Okay. If you want to be more precise, an instant input of 5 units. That way you know that I am trying to bring in the delta function here. Okay. An instant input or an impulse input of 5 units is applied at t equal to 3 and shut off. And assuming that the system starts from equilibrium, that means y of 0 equal to y prime of 0 equal to 0. Okay. That's the same as saying there's nothing happening at first. So it's just sitting there and I have nothing better to do. I just hit the system with a baseball bat and give it 5 units of force. Okay. So that's what it's going on here. Find the displacement y of t. I know it looks pretty complicated. Spring mass damping, there is a crazy function going on. Okay, but once you solve it, you'll look at it and say, "Wow, that was it." You know, and that's what the beauty of the Dirac delta function is. Okay. So let's set up the equation first. I'm going to use y for displacement. So my double prime plus c times y prime plus k times y equal to f of t. Okay. MCK, yeah. So it's going to be y double prime plus 6y prime plus 13y and f of t. This is where you have to read the question and understand it's 5 units at t equal to 3. Okay, that's going to be 5 times delta of t minus 3. If there is no force before it, then there is no force after it. Okay. So it's not a piecewise continuous function, it's an impulse instant function. So it's there exactly at t equal to 3 and nowhere else. Okay. And that leaves you with no choice than to apply Laplace transform. There is no other way to do this now. So if we are not applying that force, the system is not going to move at all, okay, because the initial displacement and velocity are both equal to 0. The only way that something is going to happen is because of this 5 units that you're imparting to it. So take the Laplace of both sides. So L of y double prime plus 6 times L of y prime plus 13 times L of y equal to 5 Laplace transform of delta of t minus 3. And since the initial values are both 0, this should be easy to plug in s square plus 6 s plus 13 times y of s. This is something that you should always double check. This part of the equation should look like your characteristic equation from chapter 2. Okay. If that does not, then you made some mistake somewhere. This is what you would have gotten if you did your chapter 2 techniques, right? Always. That would have been an r square plus 6r plus 13, which is s square plus 6s plus 13 times y of s equal to 5 times e to the power of negative 3s, and that is case number 12. Okay. There is no s in the denominator here, so don't complicate things now. Okay. Divide both sides by s square plus 6s plus 13. It's equal to 5 e to the power of negative 3s times 1 over s square plus 6s plus 13. So you expect the system to start oscillating once you hit this thing with a force of 5 units. Okay. Because it's a spring and mass, so the expectation is that once you give an external force, it will start moving. Okay. Questions to ask? Can you factor this? What do you think? No. Okay. Cannot get two numbers, so sum is 6, product is 13. At least two nice positive numbers. Okay. So what is the other option now? Complete the squares. Okay. And that's what practice does, where you get used to doing so many problems, you know what to expect in these situations. Okay, complete the squares. So it's going to be y of s equal to 5 e to the power of negative 3s. That's going to be 1 over s plus 3 whole square, which is s square plus 6s plus 9. And then you need a 4 to make up the 13. And this 4 is 2 square, obviously. Okay. So to match with one of your Laplace table cases, I think case number 8 or something, I forgot. So this is almost case number, could be wrong, it's been a while now. Almost. So 8. You need a 2 up there to make it case number 8. Okay. It should have looked like k over s minus a whole square plus k square. That 2 is missing, so you can do 5/2 e to the power of negative 3s times 2 over s plus 3 whole square plus 2 square. So now you can invert both sides. So y of t Don't forget your second shifting theorem, E becomes U, okay? And that's what I mentioned earlier. The output should start only after you give that force of 5 units. Okay? So everything is delayed by 3 seconds or 3 minutes, whatever it is. Okay? So it's going to be U of t minus 3. And this is going to be e to the power of. Can somebody online tell me what would come inside that part there? Just unmute and say, I think that'll be easier. Instead of, this is a longish kind of expression. So what do you think it's going to happen?
E to the negative 3 t.
Nobody wants to try?
E to the negative 3t sine 2t.
E to the power of negative 3
t.
T minus 3?
t minus 3. Okay. Second shifting theorem. Whenever this thing is here, it must have that same t minus a here. Okay. And then what is the other part? Sine
2t. 2t minus 3.
yes. Good. Okay. Because none of these things would have happened if you did not apply that 5-unit force. Okay. So all these things happen because of that one particular act. So everything is delayed by 3 units appropriately. Okay. And that is the final answer. So that's the power of Laplace transform and the Dirac delta function. Things get easier and quicker, okay, once you apply it the right way. Okay. Any questions on this one? Okay, so let's create a different situation. Let's turn the damping off. So a spring mass system with no damping has m equal to 1 and k equal to 9. Okay. So there are two things happening here. I turn the damping off just to keep the problem sane. Okay. So this, suppose a force of two units is applied for t greater than or equal to 4. So initially there is no force. Okay. So then you're applying a force of 2 units, but you're not really shutting it off. It's not an instant input, it's a step input. Okay. And another force of negative 3 units, it's the opposite direction, is applied at t equal to 7. Okay, that is what the hint should be, whether it's a step function or an impulse function. Okay. This is a step function because it's continuing for all the time after 4. The second one is just at a particular instant. Okay. So at t equal to 7 and shut off. And suppose the system starts from equilibrium. So initially it's not moving. Okay. Find the displacement y of t. Okay, so that's the worst possible scenario, right? You've got both the heavy side and the delta function, the same problem. Okay. So can you first write the differential equation, set it up and see what it looks like, and then I'll, once you do that, it's pretty easy to do this. Okay. So it's the first part. Setting up the problem is the challenging part here. Again, there's no damping. Okay. I think that mask was a protection from all the chalk dust. Now I'm breathing everything in. All right, so since C is equal to 0 here, okay, the equation is just my double prime plus k times y equal to f of t. So the left-hand side is very standard, y double prime plus 9y. How do we write the right-hand side here? Any suggestions to convert all that story into a mathematical problem? That's what modeling is about. Yeah.
2
Mm-hmm.
delta t minus
2 u, because that's a step function, so it's 2u t minus 4. Okay, so whenever there is greater than or equal to, that means it's not turning itself off after t equal to 4, right? So 2u t minus 4. And what about the second one? Plus or minus 3 delta. Yeah, that's the difference between the u and the delta functions. Yeah. Where the initial values are still 0, so that's a nice problem to solve. That is given in the question. You didn't have to create that, so that's what the setup of the problem is. Okay. All right, take Laplace transform both sides. It's going to be s square plus 9 ys. So since both these famous things are here in the same problem, okay, you need to look at your table carefully, copy it. Okay, so this is case number 11, and this is case number 12. One of them has a s in the denominator, one of them does not. Okay. Just need to copy it correctly, so it's going to be 2 e to the power of negative 4 s over s minus 3 e to the power of negative 7 s. Now, from an operational point of view, if you have s in one of them, at least I know that what you're, the problem is expected to kind of test on a couple of things. So if you can put this here or here, at least if you miss it on both, that's a bad thing. Okay. So if you have at least one of them, 95% of the problem is at least showing that you know everything you're doing. But try to do it right. Divide both sides by square plus 9. So I get y of s equal to 2 e to the power of negative 4s. I don't know if that 2 is useful inside or outside. Okay. Maybe I could keep it inside so that I won't forget it. So e to the negative 4s times 2 over s times s squared plus 9 minus e to the power of negative 7 s times 3 over s squared plus 9. Actually, you won't believe it, this 3 is ultra useful for this one. So. Unfortunately, what should we do here? Partial fraction. Okay. That's only inconvenience with the Heaviside function. There is that s in the denominator. Whenever that happens, you need to do partial fraction here. Okay. Mr. Dirac is good to go. There is nothing necessary to do here. Okay. Alrighty, let's see. 2 over s times s squared plus 9. So this is what I would write after the long weekend.
BS plus C.
Good. So please don't make that mistake. If you have to do a partial fraction on this, okay, the quadratic term should have a linear term on the top. Linear would have a constant. Okay. Clear the fraction. So it's 2 equal to a times s squared plus 9 plus s times bs plus c. So there is nothing unusually scary if both the functions are together. You just need to do it patiently. Okay. It's a very easy problem if you don't panic. So put s equal to 0. And you get a equal to 2/9. Now you could plug in some random values and find the remaining 2 letters. What I would prefer doing is just expand it out. That way you won't make mistakes. Okay. So it's 2 equal to a square plus 9a plus bs square plus cs. This is 9a, not 9as. Okay, that's a constant term. This is s. This is s square. So it's going to be a plus b times s square plus cs plus 9a. A plus b is 0 because there is no s square on the left hand side. Okay. C is also equal to 0 because there is no s on the left hand side. And we already have 9a equal to 2. So a is 2/9. Okay. So b is negative a. C is 0. Okay. And now we could go back to our problem and plug it in. So this is a spring mass problem that started with no damping and no initial displacement of velocity. Okay. There was some force that was given at t equal to 4, and there was an instant force that was given at t equal to 7. So it's going to create separate motions and then trying to create the system oscillating. Okay. So it's e to the power of negative 4s times a over s would be 2/9 over s. And I think I've showed this here once, that when you plug it in, make sure that the s does not disappear. It's bs plus c, not b plus c. Okay. I know it's going to happen on the test. No matter how many times I say this, it's one of those things that never goes away. So minus 2/9. So please prove me wrong. Okay. S over s squared plus 9. So that is from the first part. The second part, nothing has changed. Minus e to the power of negative 7 s times 3 over s square plus 3 square. So just to highlight that the 3 is very useful. So as expected, these external forces have created some oscillations. Okay. So y of t. Okay, let's listen to some people online. How do we start writing this solution now? Y of t. Just unmute and, or unless you want to type in the chat window. Okay.
So u into t minus 4
All right, u t minus 4
into 2 over 9
times 2 over 9
minus 2 over 9 cosine 3t. Cosine 3t minus 4.
Okay. Cosine of 3 t minus the same 4. Okay. Bracket close. That's for this. Now somebody else maybe here can tell me the second term minus. Now the instant force is coming in. All right. This is k over s square plus k square. So sine. All right. So all the output functions are delayed because you did not have these functions to start with. Okay. This was starting only at t equal to 4. This happened only at t equal to 7, but its effect is felt after that. Okay. My only suggestion, this is, we don't have an oral exam in this course, but when you say this is not a u of t times that, it's just notation. Okay. But except that, when you write it, you just write it using parentheses. Okay. That's just to tell you that you are delaying that function by 4. All right. So that's a complete example there. Okay, kind of has partial fraction, the u function, the delta function, and the spring mass problem, the second order. The only difference, the only thing that is missing was the pseudo initial values. That would have just added 2 more terms on the right side. Any questions on this one? If you can do something like this, you can do a whole lot of problems in chapter 3. Just everything. All right. Any questions? Let me kind of create a twist in this problem. Okay. Example. The same system, say m equal to 1, k equal to 9, and I'm applying this external force f of t equal to cosine of 3t for t between 0 and 2 pi. Okay, the 2 pi is magical for these functions. Okay, and 0, that means I'm shutting it off for t greater than or equal to 2 pi. If that time, instead of 2 pi, if this was some other number, it would have been a little bit more difficult to do this. That 2 pi, make a note of why we are doing this. Okay. So no damping, c equal to 0, mass, spring, external force. So part 1, write the Laplace transform for, which will kind of help you in the second part. Okay. Write the Laplace transform for f of t. Okay. One suggestion would be to write it using the step function first, using the formula that I wrote earlier at the beginning of the lecture. Okay. Step part 2, assuming that the initial displacement is 0 and the initial velocity is 0, just to keep the problem short. Okay. Find the displacement y of t. going to see some very interesting results here. Okay. So we're going to start with part one. First, write it as a step function. If you want, I can write that expression here. Okay. F1, F2. Two pieces, that's going to be F1 plus U of t minus T1. It's F2 minus F1. So that's what I expect you to use here to find the Laplace transform for this step function here. Okay. So find y of t. Again, this is the external force to the system. Okay. A small piece of trivia, if you will. Okay. The cosine function and the sine function, they're periodic with periodically 2 pi. That'll be incredibly useful here. So that's what I would get if you just apply that formula for the piecewise function as such, okay, which you can now rewrite as cosine of 3t, that is my f1. It means that you're having a force and then you're shutting it off. And then you have a minus because of this, u of t minus 2 pi. And this is what I would suggest. Since it's periodic, just write it as cosine of 3 times t minus 2 pi. Okay. That comes for free because of the nice property of cosine. You don't have to do any extra manipulations there. Okay, that is why I wrote that useful fact part. because that kind of makes it appropriate to apply the second shifting theorem. Okay. First part, which is to find the Laplace transform for that function, that would be, this term is just an ordinary term, okay. Just case number 5 or something, s over s squared plus 9. This is the one that you have to be careful about. U becomes e when you go to the right. Okay. That's minus e to the power of negative 2 pi s. There's no s in the denominator. Look at the second shifting theorem. Okay. It's e to the power of negative 2 pi s times f of s, which is going to be s over s squared plus 9. Okay. Just don't take your eyes off of the Laplace table, right? You just need to copy it correctly, s over s squared plus 9. Oh, all right. So let's go through this once more. Okay. Case 11. I'm not going to do the whole derivation, okay, but these are two different things. In case number 13, which I derived last Tuesday, or this is a second shifting theorem. Yes, there is no denominator here. Okay, there is a denominator for the individual Laplace transform of u of t minus a, but you're not really multiplying these two by themselves. Okay, when you derived it, you saw that the denominator kind of disappears. Okay. So make sure that you do not put that back in and make it worse. Okay. If you want to do the derivation again, I can do it during office hours, but it was done last week. Okay, so. All right, so that is the answer to part 1. Okay. All right, now let's do part 2. So part 2 is where the piecewise function is the external force to a spring mass system with no dashpot, okay, starting from equilibrium. So m y double prime plus k times y equal to f of t. Now that we wrote f of t in terms of the step function, we could just make use of that and write it as a single line expression. Okay. So this is y double prime plus 9y equal to this part here, cosine of 3t minus u of t minus 2 pi cosine of 3t minus 2 pi. Okay. Again, the initial values are 0, so take the Laplace transform both sides, and you get s squared plus 9 times y of s. And all those things I wrote there, okay, you just copy and paste as such. So this would be s over s squared plus 9 minus e to the power of negative 2 pi s times s over s squared plus 9. I don't know if you observed what is going on here. Okay. So spring mass system, no dashpot. You're applying this cosine of 3t here. This was k equal to 9, okay, m equal to 1. Its natural frequency was the square root of k over m. Okay, there is no dashpot here. So you have omega equal to square root of k over m, which is 3. Okay. This is also 3. What do you call that thingy? Where those two frequencies match. What is the physical name for that?
Resonance?
Let's resonate here. All right, resonance. Resonance brings in all kinds of problems, okay? But Laplace transform helps you solve this in a jiffy. Let's see. Okay. Divide both sides by s square plus 9. And you get y of s equal to s over s square plus 9 whole square. Okay. Pay attention to this one. Okay. Very important stuff. S over s square plus 9 whole square minus e to the power of negative 2 pi s times s over s square plus 9 whole square. Oh, you kind of start scratching your head. What should you do now? Should you do partial fractions or completing the squares? Well, it's already a square. You can complete the squares. And if you look at your Laplace table carefully, you will see something which is very, very similar to these two terms. All you have to do is look, and you will see. You might see something like this. That's when I say very, very similar. K is a constant. We can always bring it in as we like. Okay, something with 2ks over s square plus k square whole square. I hope it's there. And that what number is that? Case number 10, or we have never used that case, so you have to kind of, case 9 or 10? 9. So here k is 3. Okay. There is nothing here, so you have to somehow create a 2k. So 2k is 6. So you can write this as 1/6 times 6 s over s square plus 3 square square minus e to the power of negative 2 pi s times, again you can divide by 6, multiply by 6. Okay. That's what you get. And what is the Laplace inverse of this term according to case number 8? There's no need to shift the first term. Okay, there is nothing multiplying it here. So you just need to tell me the raw inverse from the table. What is that?
T sine of.
Yes, t sine 3t. Okay, this is what happens during resonance. The amplitude just keeps going up to infinity as t goes to infinity, right? If you were doing this using chapter 2, you have to write xp equal to t sine 3t plus t cosine 3t and do all that stuff. Okay, this is automatic. Minus 1/6. Remember that e becomes u. Okay, so it's going to be u of t minus 2 pi times the same term, but it's shifted by 2 pi. Okay, so instead of writing t sine 3t, it's going to be t minus 2 pi sine of 3 t minus 2 pi. Just make it clearer here. So it's minus 1/6 u t minus 2 pi times t minus 2 pi sine 3 t minus 2 pi. Barely. Okay, there you go. The most important thing you have to observe from a physical point of view is that as t goes to infinity, this is a bad thing. Okay. That's amplitude which is growing with time. Eventually the system will break if you just let it go. Okay. This is resonance here. But in terms of writing the answer, you could stop here. Okay. If this was maybe on a quiz or a test or something, I don't expect you to do any analysis of this. Okay, that is fine, but it's useful to study what is really going on in this problem here. Okay. So the meaning of the solution is the following. Remember that you have that force for t equal to 2 pi and then you shut it off. Okay, so that should somehow appear in the solution. So u of t minus 2 pi is equal to 0 for t less than 2 pi, and it's equal to 1 for t greater than or equal to 2 pi. Okay, that is the meaning of the Heaviside function, right? So if you look there, you have y of t. When u of t of minus 2 pi is equal to 0, the entire second term is 0. Okay. This entire block here, that becomes 0 for t less than 2 pi. So you just have the first term, which is 1/6 t sine 3t. And assuming that you're starting from t equal to 0. Okay. So there is resonance for the first 2 pi units of time when that external force is applied. Okay, things are going crazy here. But once the force is turned off, which means that u of t minus 2 pi is equal to 1, okay, then you have 1/6 t sine 3t minus 1/6. Remember that term is 1 now, okay, times t minus 2 pi, and sine of 3 times t minus 2 pi is the same as sine of 3t. Yes, again, sine is periodic with 2 pi. Okay. And if you simplify this term, this becomes 1/6 t sine 3t. The first block of terms would be minus 1/6 t sine 3t. The second one would be negative 1/6 times negative 2 pi, which is pi over 3. Okay. Sine of 3t. So this means that as soon as you shut off that force, there is no more resonance. Okay. This is a constant amplitude from that point. Pi over 3 is a number, right? So this craziness stops as soon as you shut off that force cosine of 3t that is applied till t equal to 2 pi. Okay. So there is resonance here, no resonance here. So that is the meaning when once you start the solution and then just look at it term by term, okay, it should have complete sense with the physics of the problem. Otherwise, there is no meaning to doing this. But you're not expected to do all that stuff. Okay. You can stop with that boxed part there, but it's a very important example. Please don't ignore this when you study for the test. All right, so I think that will be a good place to stop. I think I did enough examples with the U and the delta function, spring mass. Okay, do the homework. If you have any questions about any particular homework question, you can bring it to lecture tomorrow. I think I have some time to kind of wiggle around here. I'm not completely tight with time. So if you have any particular homework questions you want to do, just bring it to lecture. Okay, so up to here for test number 3. So you should know how to find Laplace transform inverses with and without the U and delta functions. Okay. So we'll start linear algebra tomorrow if you don't have any questions. So test. All right, so that will be the end of today's lecture, and I can stay back if you have any questions you don't want to discuss over the recorded video. Okay, I can stop recording.